Welcome to an exploration of TiDAR, a groundbreaking approach that finally bridges the gap between speed and quality in large language models. In this presentation, we'll dive into how combining diffusion and autoregression can unlock new levels of performance, as demonstrated on NVIDIA H100 hardware. To understand the problem, let's look at the limitations of our current hardware. GPUs are incredibly powerful, but when decoding large language models, they often become memory-bound. It's like having a massive bodybuilder, the GPU, constrained by a tiny task that doesn't let it flex its full muscle. Efficient token processing is key. Ideally, we want a system that handles tokens like a smooth roller coaster ride, continuous and fast. As we see here, the goal is to process more token slots with minimal increase in latency, keeping the ride thrilling but efficient. In the race for better models, we've seen several contenders. Standard Autoregression is slow like a tortoise but steady. Pure diffusion is fast like a rabbit but can lack coherence. And speculative decoding attempts to find a middle ground, but each has significant trade-offs. Enter TiDAR, the hybrid. Think of it as a dual-process brain. One half uses diffusion for parallel drafting, rapidly generating ideas. The other half uses autoregression for sequential verifying, ensuring those ideas make sense. It's the best of both worlds. This is realized in the single forward pass machine. It's a unified mechanism where prompts enter, go through verification and drafting stages, and emerge as verified text with new proposals, all in a single streamlined pass. Under a microscope, TiDAR employs a hybrid attention mask. This clever matrix combines causal attention, looking back at what's been said, with bidirectional attention, allowing for a richer, more context-aware processing strategy. We also utilize a full masking strategy. Unlike traditional noise methods, this approach systematically masks and reveals information, guiding the diffusion process to fill in the blanks with high precision and coherence. The engine driving this is the self-speculative generation cycle. It's a continuous loop. Draft the content, verify it, apply rejection sampling to filter errors, and repeat. This cycle ensures constant quality control at high speed. Think of computational efficiency like a well-organized filing cabinet. Accepted tokens are neatly filed away, while rejected ones are immediately discarded. This means there's absolutely no wasted compute. Every cycle counts. The results speak for themselves. When we compare standard autoregression against TiDAR models of 1.5 billion and 8 billion parameters, the increase in speed and tokens per step is substantial. TiDAR simply moves faster. But what about quality? You might think faster means worse, but that's not the case here. As this illustration shows, the quality between slow AR and fast TiDAR is practically indistinguishable to the user, backed by solid benchmarks in coding and math tasks. We are effectively closing the gap. Traditionally, there's always been a painful trade-off between quality and speed. TiDAR breaks this curve, offering a new optimal point that delivers on both fronts without compromise. It's time to sweep away old assumptions. We used to believe that high quality inevitably meant high latency. TiDAR proves that these deployment assumptions are outdated. We can have our cake and eat it too. In conclusion, TiDAR does the heavy lifting, managing tokens with strength and ease. It represents a significant leap forward in LLM architecture, delivering the speed we need with the quality we demand. Thank you.